So, I will speak in English in respect of for our invited speakers. I was in charge to give this lecture, but actually a group of people is involved in the construction of the icing wind tunnel of this university. So actually this is one of the topics of José Roberto's PhD. So he's almost finishing his PhD here at COP, but actually Paulinho and lots of undergraduate students were involved in this project. So just to give a brief historical perspective, in the morning we mentioned the previous seminars regarding aviation safety. So the idea of the wind tunnel actually was brought up between the first and second seminars of aviation safety, workshop of aviation safety. So the workshop came up by a group of scientists from Brazil, United States, and France. Actually, Professor Sheriff and Professor Bob were here in the first workshop of aviation safety, and the ideas that came up on those two events actually resulted in the wind tunnel. So I was going to say that, Bob, don't worry, your email account was not intercepted by the National Security Agency. This message came to me by Professor Attila, and actually I apologize to bring up a personal email, but it's just to contextualize, just to put in context the idea of building up an icing wind tunnel here at Skopje. So in this email was sent by Professor Bob to Renato, and here he mentions that it would be a good idea to build up an icing wind tunnel in Rio, and it would allow us to do serious research on icing problems related to the aeronautical industry. And actually here I will. So, I beg your pardon. Just to stress some points. Actually, Bob gave all the clues for us. It was a good idea to build up an icing wind tunnel. So an icing wind tunnel need not to be big. Actually, space is one of our crucial limitations. Actually, our current lab is almost full, and the next one will be full in some years to go. So we didn't have too much space, but here he explains that since the pitot tube is a small, flow blockage is not a problem in a small wind tunnel. So since the pitot tube is small, the tunnel could be small too. And the icing wind tunnel would be perfect for research on conventional pitot tubes, and also in new technologies or new sensors for velocity measurements, sensors that are not so prone to icing problems. So we got this idea, and Attila is also a crazy person. He always says that he has nothing to do, so he sent Bob's email to me saying, we are going to build a new wind tunnel. So, okay, we started planning that, and actually FAPERJ, our scientific foundation of Rio de Janeiro, opened a scientific call in September 2011. And if you check, this email was sent in May, and in September we had a sketch of the wind tunnel. So here is a very basic sketch, but actually resulted almost in the real wind tunnel we have today. So I will explain this in detail, but it's just to give an idea of time schedule. We sent a proposal for FAPERJ at September 2011. And actually, a place to receive the wind tunnel was selected in November 2011. The building next doors you have just visited. It was like that in November 2011. Actually, the boats are still there, but now we have also the wind tunnel operating. So then in August 2013, we had a big part of the wind tunnel already made. So it was made by stainless steel tubes. We had already the test section in place, and here we can see the other wind tunnels over there. So the condensers and things were going on. And then in May 2014, actually, in the beginning of this week, the place we have just visited was like that. We were crazy about the schedule because we wanted to make everything ready for this workshop. Actually, the date was very important for us, and everything should be ready by the time. And this was actual teamwork. So when everybody involved wants to make it happen, we can make it happen. And in 2 days' time, everything was working, and we managed to turn on the wind tunnel yesterday. And as Professor Cota mentioned, the Murphy's Law was not valid for this time, and we could turn on the wind tunnel, the fan, the cooling system, and actually we managed to generate ice in our wind tunnel. We have the pitot tube installed over there, and actually it was this picture was taken 8 p.m. when the experiments were done. Everything were closed together, and we were very happy because everything worked as we planned. So coming back to the initial concept of the wind tunnel, since the space was an issue, we planned to build a closed wind tunnel distributed vertically, actually with the fan located on the upper side. So we would let the flow develop. Here would be placed the cooling system, and then we have directing vanes, the honeycomb, contraction, and the test section. But actually here we have the details. The fan, as I just mentioned, the heat exchanger, and the spray bars to generate the particles. Actually, this configuration had a small problem because of the fan. In this, I don't know if you noticed, but in this configuration, we had to let the axis vertically, and this had some mechanical problems that the company that would provide us the fan would not like to resolve. So we simplified the problem and relocated the fan. And I will show you how we got to the final version. So our basic idea was to build a closed and vertical wind tunnel. Since the space was an issue again, we have that first figure I just showed with the boat. That was the place we had to fit the wind tunnel. So it should have 7.5 meters in length and 3.5 meters in height. It would be made of stainless steel to resist the water and the droplets we would insert. And we would like to reach 58 meters per second, or Mach about 0.2. I didn't put the Reynolds number. I agree that Reynolds number is a critical number, but Reynolds number is a not well-defined number. We could define based on the height of our sensor or on the diameter of our sensor, so that's why I didn't include it here. In the temperature range, we would like to reach minus 20 degrees, and it will certainly go this far. So, as I mentioned, the refined configuration, we relocated the fan, but the basic structure was the same. So we would have the flow going through the contraction, the honeycomb and the screens to the test section, and then, oh, I beg your pardon, this is the other way around actually. And then the heat exchanger would be here on the upper side. So, the final configuration, we managed to get it a bit larger than, or bigger in length as we first planned. The cross-section of the main wind tunnel is 0.8 per 0.8, so as the bigger the section, the lower the lower drag we have, so the lower the pressure drop we impose to the fan. So that's why we chose those numbers, and those numbers also allowed us to have a contraction of a rate of 7:1. I will show you later. And so the configurations were mainly the same. We could construct what we had in mind in the first place. And this is what we have right now. So you have just visited there. Actually, we have to just relocate the position of the fan because of restrictions of this space here and the product that we could easily find on the market. So, but these were planned according to what we have in the literature. And here we have the diffuser. So the flows goes in this direction. The fan lets the flow to the heat exchanger. Then we have directing vanes here. Here we have the honeycomb and screens to direct and uniform the flow, and then the contraction. So right now I'm going to talk a little bit of each of those components so that we can have a general idea of power that we have here and how those parts were specified. And then what we expected to get from this equipment. So the propulsion system, actually power is also an issue for that lab because it will receive lots of huge machines and pumps and so on and so forth. So we had to limit our maximum velocity in order to get a fan that we could feed. So in terms of energy. So we specified a fan that could provide us Mach 0.2, so we actually went the other way around. We checked how much pressure the fan could provide, and then specified the honeycomb and quantified all the pressure drop in the system. So José Roberto did all those calculations, and actually this is part of his PhD. So the fan has those dimensions and this weight and this power in final, and we can vary the velocity in the wind tunnel by frequency inverter, changing the rotation of the fan. So the cooling and heating system, the idea was to we did all the calculations of how much heat we would have to extract from the flow and from the water droplets we insert on the wind tunnel. So summing up all the terms of that we had to exchange, we came up to this number. So the evaporator unit has this capacity in order to provide minus 24 degrees Celsius for that test section. The working fluid is this refrigerant fluid, and the two condenser units are positioned on the top of the lab. And it was a huge operation also to take the condenser units to the top, because they weight a lot and have this power each. So we are operating now just with one. They can be used in parallel, so they can be both turned on in order to provide a lower temperature on the test section. And we also have a heating source for the pitot tube in order to test the resistances and the performance of the de-icing or the anti-icing systems of this pitot tube. We are actually focusing right now, but we are also planning to have the capacity to heat other components that we want to study. So, and we also have a power to feed some electrical resistances that actually are heating the veins that comes directly downstream of the test section. So the idea is to liquefy all the supercooled droplets that goes through the test section in order to avoid water going through the fan. So here is a picture of the condenser being set up on the vertical section of the wind tunnel, the two condenser units that were positioned afterwards on the top of the lab, on the top of the building, and here the vanes being installed on the wind tunnel. Actually, these vanes were also dimensioned, and each of them has a specific, follows a specific curve dimensioned according to the recommendations on the literature. So here is a picture of the condenser on the top and the connections between them. So our basic reference was the book, actually, of those two researchers, Wind Tunnel and Their Instrumentation, from the 60s, a classical book where we can find all the mathematical equations and modeling to predict the vanes, the screens, and the honeycomb, which are the main sections of the wind tunnel. Okay, so the guiding vanes, the purpose of them, this is especially for the students that are coming up to know a new apparatuses, and it's interesting to know how those the parts that build the whole wind tunnel works. So we call those elements the flow conditioning elements in order to have a high quality flow on the test section. So the purpose of the guiding vanes is to straighten and smooth the flow downstream of the corner. Since we have a closed loop wind tunnel, we have to be careful about that. So downstream of the test section, the guiding vanes are used to cool the droplets, what I have just explained. So the idea is to heat those vanes, and initially we were going to use like sections of an airfoil, but it became a bit complicated to shape, to build the actual shape of the airfoils and so on. So we tried to simplify everything, and now we are going to do the experiments to check the flow on the test section, and we are going to change things as it's needed. But we use it actually fins that are just a plate modeled according to the shape of the corner. So these were heated by electrical resistances, and the purpose is to make the flow uniform after the corner. The screens in the honeycomb, they are used to straighten the flow and break up the large vortices. So here we have an illustration of how the porosity of the mesh and how the diameter of the elements of the mesh alter or interfere in the uniformity of the flow. So actually we have to choose the best screen to make the flow uniform on the test section. So this was dimensioned. Our screen and our guiding vanes were dimensioned according to the recommendations given in this book. And actually all the pictures I have illustrated here come from that reference, okay? So the idea is to have a mean flow uniform and a controlled level of turbulence on our test section. So the last conditioning element is the nozzle or the contraction. So the contraction actually controls the level of turbulence on the test section. So the higher the contraction ratio, the smaller the turbulence on the test section. It's like a rule of thumb. And here we have a contraction of 7, so this is a good number. Indeed, a number higher than 5 is very good. So we have a profile designed like a 3-degree polynomial. Its total length is about 1.5 meter. And this is actually the curve that gave origin to the contraction we have there today. And the spray bar system is actually one of the main parts of the wind tunnel. This is being installed. Actually, this is the sole part of the wind tunnel which is not fully operational right now. So the idea is that it must be, the small droplets must be inserted very carefully in order to simulate the conditions of the atmosphere, so of the clouds that are prone to generate icing conditions on airplanes and so on. So here we have just very basic sketch just to illustrate that we are going to insert our nozzles in an airfoil shape in order to minimize perturbations on the flow, and those nozzles will be distributed along the cross-section of the wind tunnel in order to provide a uniform particle distribution on the test section. So here we have the place where the nozzles will be inserted, actually just prior to the contraction, in order to get a uniform cloud or a uniform dispersion of the droplets on the test section. So our purpose is to simulate droplets on the range just mentioned on the previous presentation, between 10 to 120 microns. This upper limit here actually simulates the superlarge droplets, which are the main crucial or the main problem we can face on the field application, and the liquid water content to generate those range of diameters of droplets on the test section is about this one. So we are planning to use 6 horizontal bars with distributed nozzles in here, 20 distributed nozzles in those 6 bars. And each line will be fed individually by water and an air compressed air in order to control them individually and have the capability of varying the diameter according to the experiment we want to simulate. And the temperature control is very important to avoid early ice formation. In most of the experiments, we want to have the droplets on the liquid phase reaching the model and just turning into ice on the model surface. So this needs high temperature control of both the temperature on the wind tunnel and of the water droplets inserted on the spray bar systems, inserted here in this place. So the test section has 300 millimeters in both height and width, and 2 meters in length. So this allows us to study the pitot tube geometry, but also airfoils and different aeronautical structures. So as I mentioned, we are managing to reach negative temperatures already. So I made a zoom of our temperature monitor here. Actually, this is the temperature inside the test section being monitored by a thermocouple. And the test section, as you just saw, is fully instrumented. So we have an infrared camera here, the pitot tube installed on the test section, the LTA, and also the laser for the PIV in here. And this is I had just a picture from the construction work, but here we can see how we can reach the inner part of the test section. Actually, we opened the top side of the wind tunnel in order to introduce the models and the inner part of the test section. Since we want to use optical techniques to quantify the velocity profile and also the particle size of the droplets, we need the test section to be transparent. And we also must be careful with condensation of humidity on the side walls or the whole walls. So the idea was to introduce some electrical resistances. Actually, we have free distributed resistances and a free glass walls. So we have like a sandwich of 3 layers of glass and a hollow space on the middle. And this is a zoom of the electrical resistance that's placed on the face of the glass. So these are already working. We have to check if those 3 are actually enough to prevent humidity condensation, so that we can use LDA and PIV for velocity measurements. So this will certainly be an issue. So the diffuser, I don't know if you had paid attention, but I'm just going, I'm doing the flow direction. We move it from the fan to the condenser, then to the honeycomb, to the screens, to the test section, and now we are going to see the diffuser. So the diffuser is the element that connects the test section to the cross section that will reach eventually the fan. So Bob also mentioned he was aware that we should not put a high angle in the diffuser in order to avoid separation. So this diffuser has an angle of 7, so we are just about the limit of having considerable separation, But actually, we are going to check if separation is an issue here, and if it is, we can use vortice generators in order to avoid losing energy with separation region here. But this was actually dimensioned according to the literature again. So what's the instrumentation we are intending to use? As I just mentioned, we are mainly relying on laser techniques. So this is the ideal instrumentation for a wind tunnel because it's non-intrusive and we can measure velocity profile with high temporal and spatial resolution. So we have all those instruments fully operational on the lab. So we have LJ systems, PAV systems, hot wire systems, scientific pitot tubes. And for the temperature measurements, we are seeing here the infrared image obtained yesterday on the wind tunnel, thermocouples and resistive thermometers. And in order to measure the droplet distribution, we can use the PDA, which is also fully operational. The PDA can measure diameter distributions from the lower micron range. Here, you probably cannot reach the legend here, but we are here measuring from 1 micron to 4 micron distribution. And the PDA can also reach about 1 millimeter, 1.5. So this instrument is actually very reliable and it covers all the range of size distributions we need to quantify for the pitot tube case. And also high-speed cameras if we have large droplets as we see here. So this is why we could make the wind tunnel fully operational with a very low budget. So actually this wind tunnel was designed and constructed with national technology. So our students, our undergraduates, and our PhD students did all the calculations, did the heat transfer calculation, the friction factor calculation, the pressure drop. So we paid nothing for the project, for the knowledge involved here. And we hired a local company. We teach them how to construct the wind tunnel. So we have everything working for a very small budget. And this is another thing to be stressed. Knowledge also costs a lot. So if we would import a wind tunnel, it would be millions in millions of dollars or euros or so on. So, and all the instrumentation was previously available because if you sum up the cost involved here, it's a lot. So, the wind tunnel capabilities, what we can do right now, and Zé Roberto is going to start doing in his PhD thesis next Monday. So we are now able to reproduce extreme weather conditions under controlled laboratory experiments. So we have seen all the open questions and all the demand we still have for understanding how icing on aeronautical structure occurs. So we can, having the wind tunnel fully operational, we have the ability to contribute on this issue. We can also simulate natural icing conditions in order to, this will be reproduced by injecting water droplets into the air stream via a spray bar. So here are the types of icing geometries we can simulate. So this is a thin layer completely distributed in the airfoil. Here we have accumulation on the leading edge, and then a geometry that really alters the boundary layer on the airfoil, compromising the lift, and so on and so forth. So the simulation of ice accretion on aeronautical sensors, in particular the pitot tube and mechanical structures. And we will be able to investigate, do the modeling and develop new sensors and materials for aeronautical structures. And also test anti-icing and de-icing mechanisms or techniques. So we can contribute in different areas related to the subject. And our idea is to contribute actually in each of those subjects. We are already working on surface deposition films, which actually can be hydrophobic and avoid the deposition of the water droplets on the surface. We are also working on developing new sensors based on optics, for example, that are not so prone to icing restrictions like the pitot tube. And the wind tunnel will also be extremely important to generate an experimental database for validation of mechanical models and numerical codes. So we have our group, as Renato and José Roberto has also developed some mathematical modeling of the problem that needs to be validated against reliable results. So the importance of doing our own experiments is that we have conditions to quantify all the variables we need. Anyone that has already needed experimental data from other researchers know how difficult it is to gather all the variables we need to validate our models. So this is the importance of having everything done. So here are some references. Obviously, NASA Glenn Research Center is one of the main references. Here is a sketch of the inner parts of the nozzle of the spray bar system that we intend to reproduce something similar of that. And just to conclude the presentation, this is as it was mentioned in the beginning of the seminar, this is the first wind tunnel of the southern hemisphere, as we know, as far as we know. So this is not a small thing, and we have to learn to value the results we get. So this is one of the ideologies of this graduate school. Do much work with think big and act small. So thinking big and acting bit by bit, we can reach the result. And having a good team is involved with the purpose, and working together, we can do very big things. And this is one of the big things we can be proud that we reached. So with our team. We will also, as I mentioned, we are investing on developing new techniques of anti-icing and de-icing systems, new sensors, and generating a reliable database to validate models and eventually propose solutions for the industry. And it will be a pleasure to collaborate also with important centers as Boeing Research Center and all the invited speakers here. So thank you for your attention, and should you have any questions, I'll be pleased to respond.